Hello, everyone, and welcome to today's live webinar, Choosing the Right Protein Gel for Your Research Application, presented by Dr. Alok Tomar, Product Manager for Thermo Fisher Scientific. I am Marjorie Torres, and I will be your moderator for this educational webcast, presented by LabRoots and sponsored by Thermo Fisher Scientific. Before we begin, I would like to remind everyone that this event is interactive. We encourage you to participate by submitting as many questions as you want at any time you want during the presentation. Just click on the green Q&A button located in the lower left of the presentation window and type your question into the box that appears on the screen. We'll answer as many questions as we have time for at the end of the presentation. Also, please notice that you will be viewing the presentation in the slide window. To enlarge the window, just click on the screen icon located on the lower right. If you have trouble seeing or hearing the presentation, please click on the support button at the top right of the presentation window, or use the Q&A button to let us know that you're having a problem. This is an educational webinar and thus offers free continuing education credits. After the webinar is over, please click on the CE button located in the bottom left-hand corner of your webpage and follow the process of obtaining your credits. Please join me in welcoming Dr. Tomar, and I will now turn the presentation over to him.
Hello everyone, and welcome to this precast protein gel webinar, where we will review how best to choose the right gel for your research application. This is the brief agenda for today's talk. I'll be talking about different types of protein gel electrophoresis with emphasis toward different gel chemistries of precast gels and their specific applications. I will also talk about how precast gels can contribute to protein modifications during electrophoresis, followed by how that information will help in selecting the right gel for a specific research application. And finally, I will go over a few slides highlighting improvements within precast gel options. This is Protein Gel Electrophoresis 101 that lists the frequently used types of protein electrophoresis. As you know, PAGE stands for polyacrylamide gel electrophoresis. In a native PAGE application, ionic detergents like SDS are not added to any of the buffers, resulting in the charged proteins being separated according to their native physical properties in an electric field. SDS is an ionic detergent, and when added to gel electrophoresis buffer, it denatures proteins and binds to this denatured proteins, providing a uniform negative charge to all proteins, which facilitates separation according to size only. As shown in the schematic to the right, the SDS detergent in presence of reducing agent can separate the two subunits of a protein that are held together by disulfide bond. Reducing agents like DTT or beta-mercaptoethanol can reduce disulfide bridges to achieve better denaturation. The negatively charged SDS molecule then binds uniformly to entire protein, which results in a separation according to the size of the protein only. The smaller subunits would migrate faster, as shown by subunit A migrating faster than the bigger subunit B, thereby creating a size-based separation on the slab of polyacrylamide gel. This is a quick schematic of what happens during SDS-PAGE. Addition of SDS to the protein results in denaturing of protein, followed by uniform binding of SDS to amino acids, providing uniform negative charge. Heating of the sample prior to loading the gels results in uniformly charged linear protein in the sample buffer. Protein samples are then added on to the gel and electric current is applied that causes migration of negatively charged protein towards the positively charged cathode. The distance traveled by proteins is directly proportional to the size of the protein. Precast protein gels are available as either constant gel percentages like 8%, 12%, 12%, 8%, 10%, 12%, etc., or as gradient gels, which can be 8 to 16%, 4 to 20%, and so on. The size of the target protein is used to determine which gel percentage to use. Smaller proteins require a higher gel percentage for optimal separation and vice versa. The advantage of a gradient gel is that it can be used to separate a mixture of different molecular weight proteins in the same gel. A gradient gel has different layers of gel percentages as shown in the schematic, with higher percentage at the top and lower percentage at the bottom. The layers of these different gel percentages allow for optimal transfer or optimal separation of a wide range of protein mixture which can't be achieved using a constant gel percentage. Okay, so in next few slides, we will review the different gel chemistries that are available in precast gels and the specific advantages and disadvantages. The two most widely used gel chemistries are Tris-Glycine, which uses traditional lamellar buffers, and the Bis-Tris chemistry. The other two specialized gel chemistries are Tris-Acetate gel chemistry, which is specialized for separation of large molecular weight proteins, up to 500 kilodalton in size, and the Tricine gel chemistry that is specialized for separation of peptides and small molecular weight proteins. Peptides as small as 2.5 kilodalton can be resolved using the Tricine chemistry. Let's take a quick look at the buffer system of gel electrophoresis. The continuous buffer system utilizes the same buffer in the gel and the gel running buffer. The discontinuous buffer system, which is utilized by most commercially available gels, has a different gel buffer, and the gel running buffer, they both differ. It has at least 2 gel layers of different pore sizes, and has different buffer composition for the stacking gels, which condenses the protein samples into a nice tight band during electrophoresis, and the separating gel, which is responsible for creating the size-based separation of protein samples. This slide provides a quick summary of the discontinuous buffer systems utilized by the 3 most popular gel chemistries. The Tris-Glycine system includes tris and chloride ions in the gel buffer, which has a pH of 8.7. The running buffer ions are tris, glycine, and ionic detergent SDS with pH of 8.3. Importantly, the gel operating pH for Tris-Glycine system is 9.5. Therefore, this is a very alkaline gel operating environment. The common ion in this system is tris, which is present in the gel as well as the running buffers. The Bis-Tris system includes Bis-Tris and chloride ions in the gel buffer, which has a pH of 6.4. The running buffer ions are tris, mes, or mox, and ionic detergent SDS with pH of 7.3. Now, importantly, the gel operating pH of Bis-Tris is 7, which is a neutral gel operating environment. The common ion in this system is Bis-Tris. The Tris-Acetate system includes tris and acetate ions in the gel buffer, which has a pH of 7. The running buffer ions are tris, tricine, and ionic detergent SDS with pH of 8.3. The gel operating pH of the Tris-Acetate system is 8.1, which is slightly alkaline, but not as much compared to the Tris-Glycine system. Now, the reason why gel operating pH is important is because pH plays an important role in protein modification that can happen during electrophoresis. The precast gel and its buffers are not really an inert environment as sometimes perceived. The electrophoresis process can result in modification of your protein of interest, which can have impact on downstream applications following electrophoresis. For example, deamidation is a chemical reaction in which an amide functional group in the side chain of asparagine or glutamine is removed or converted to another functional group. Deamidation can lead to protein degradation by affecting its structure, stability, or function. This reaction also results in a mass shift of +1 Dalton. Similarly, addition of sulfhydryl or amino group to the acrylamide have been reported in Tris-Glycine gel formulation, and amino groups are known to react with acrylamide at basic pH. The study, which is shown on the right, was published in Analytical Biochemistry, and it looked at reaction of glutathione with acrylamide in various buffer systems. Tris-Glycine buffer system with pH 9.5 showed the highest level of glutathione modification, whereas Bis-Tris or Tris buffer system with pH 7.2 essentially showed none or minimal glutathione modification, as represented by solid or open circles at the top. Therefore, the alkaline pH of Tris-Glycine buffer system results in significant protein modification compared to neutral pH Bis-Tris system. So in the next few slides, I will discuss the different gel chemistries of precast gels and their advantages. As we have discussed already, the Bis-Tris gel chemistry has a neutral pH operating system which plays a vital role in minimizing protein modification and protein degradation, thereby preserving sample integrity. Since the Bis-Tris gel chemistry is comparatively less reactive with acrylamide, the Bis-Tris gels have a shelf life of up to 16 months at room temperature. A Tris-Glycine gel can be stored at room temperature because of its higher reactivity and its comparatively shorter shelf life. It is also known for quite some time now that a neutral pH environment during electrophoresis improves protein stability, which enables sharper band resolution and provides accurate results. This slide shows comparisons of the same samples which have purified protein kinases implicated in cancers, which are loaded on Invitrogen Bold Bis-Tris Wedgewell gels and Biorad Tris-Glycine TGX gels. Since Bold Bis-Tris gels have a neutral gel running pH environment, the sample integrity is preserved and protein degradation, if any, is very minimal. However, the Biorad TGX gels, multiple degradation bands are detected along with the full-length purified proteins. This demonstrates that the Bis-Tris chemistry with neutral pH minimizes protein degradation during electrophoresis. Now, the Tris-Acetate chemistry is specialized for optimal protein separation and transfer of high molecular weight protein, as high as 500 kilodalton in size. If you are working with high molecular weight proteins like EGFR or EGF receptor, BRCA, or some other larger membrane proteins, this is an ideal gel chemistry for such applications. Migration charts are provided by all precast gel chemistry vendors, and they are a great resource in deciding which particular gel chemistry or gel percentage within a chemistry will be optimal for your protein of interest. Since a Tris-Acetate gel can separate the high molecular weight protein better, it is able to move these bigger proteins more towards the center of the gel, and they are not all stacked at the very top near the stacking gel. Since those larger proteins are brought a little away from the stacking gel, the transfer efficiency with a Tris-Acetate is also better. So the image on the right shows detection of EGFR receptor at reducing lysate concentration from left to right. The new page Tris-Acetate gel on the top shows significantly better transfer efficiency and sensitivity of detection compared to Tris-Glycine gel at the bottom, which is really not an optimal chemistry to detect high molecular weight proteins. Now, on the other hand, if your interest is in detecting low molecular weight proteins and peptides, you should use the Tricine chemistry that is optimized for separation and transfer of low molecular weight proteins. As demonstrated in the migration chart, the Tricine gel enables the smaller molecular weight proteins, like caspase subunits in this example, to be optimally resolved closer to the middle of the gel compared to a Tris-Glycine chemistry. As seen in the image on the right, the Novex Tricine gel on the top provides a very distinctive separation of the cleaved caspase-3 subunit compared to the Biorad TGX gel at the bottom. Additionally, smaller molecular weight proteins experience very high blow-through during the transfer process, which means that the smaller molecular weight proteins are blasted past the PVDF or nitrocellulose transfer membrane and are completely lost, resulting in a non-optimal transfer condition. The ion concentration is significantly higher at the bottom of the gel near the diaphragm. Therefore, this area experiences disproportionately high current during transfer, which causes the blow-through effect. The Tricine gel provides separation of the smaller molecular weight proteins closer to the middle of the gel, thereby preventing the blow-through effect to a much greater extent, which increases the transfer efficiency. The Tris-Glycine gel chemistry is the most widely used gel chemistry and is used for a broad range of protein separation. It does have a high alkaline operating pH. Since Tris-Glycine is a very reactive gel chemistry that results in protein modification due to chemical alteration and reoxidation of amino acids, as reviewed in the previous slides. It can cause band distortions, loss of resolution, or increase background during Western detection because degraded proteins are detected by a particular specific antibody against the target protein. We understand that Tris-Glycine chemistry has its limitations, and we strongly recommend that it should not be used for every application in your lab. The one-size-fits-all approach is really not optimal or efficient when it comes to selecting a precast gel for different research applications. Having said that, we have worked really hard to overcome some of the limitations of Tris-Glycine chemistry while utilizing its inherent advantages. The Novex Wedge-Well Tris-Glycine gel is designed to provide excellent band resolution, sharpness, and staining efficiency compared to Biorad TGX gel. You can see better separation of multiple protein bands in a live state, and the Novex TG gel also shows relatively lesser protein degradation of purified proteins. The protein bands are sharp and straight and does not show the smiling of bands, particularly in the first and last lane, which is very visible in the Biorad TGX gel. So in the previous slide, we saw the effect of gel chemistry and pH on sample integrity. In the next 3 slides, we will review the impact of sample prep on protein integrity. The image on the left is the new-page Bis-Tris gel with various sample prep conditions. The lane 2 has recommended sample prep conditions for new-page, which includes mixing the sample with new-page sample buffer and addition of 1x new-page reducing agent, which is essentially DTT, and boiling the sample at 70 degrees Celsius for 10 minutes. This provides optimal protein denaturation and reduction of Bis-Tris gels. Under this optimal sample prep condition, as demonstrated in lane 2, there is very minimal sample degradation and protein integrity is maintained. However, use of XTRA, which is the Biorad criterion XT reducing agent instead of DTT in lane 3, and boiling the samples for 95 degrees Celsius for 5 minutes, as recommended by Biorad sample prep protocol, results in significant protein degradation. The use of Tris-Glycine sample buffer with 50 mm DTT and boiling the sample for either 95 degrees Celsius for 5 minutes or 85 degrees Celsius for 2 minutes reduces sample degradation significantly, as shown in lane 5 and 6 respectively. The image on the right shows the effect of sample prep on protein integrity when using a Tris-Glycine gel. Compared to this Tris gel, the Tris-Glycine gel shows more degradation, but the choice of sample buffer, reducing agent, boiling temperature, and boiling time has a big impact on protein integrity and degradation levels. TCEP, or Tris-2-carboxyethyl phosphine, is the reducing agent present in Biorad criterion XT reducing buffer. This slide shows different prep methods using TCEP and its impact on sample integrity. Lane 2 has the recommended protocol for new page Bis-Tris gel with new page sample buffer 1x TTT followed by boiling at 70 C for 10 minutes. Lane 7, 8, and 9 demonstrate that heating the samples in presence of Bio-Rad XT reducing agent, which contains TCEP, results in significant protein degradation. This slide demonstrates that the reducing agent TDP, or tri-N-butylphosphine, at different concentration is equally effective as DTT in preserving sample integrity. However, Bio-Rad XT reducing agent in lane 9 again results in significant sample degradation. So with all this background information on gel chemistry and sample prep, we can now ask this question of which gel is right for your specific research application. Now, this table provides a quick overview. If you are working on applications like post-translational modification, which includes tyrosine, serine, or threonine phosphorylation, or if you're working with downstream mass spec application, or if your target protein is a low abundance protein that requires maximal sample integrity, then you should choose the Bis-Tris gel. Now, Bis-Tris gel will not only help with preserving sample integrity and reducing degradation, but it also minimizes protein modification during electrophoresis. That can have a significant impact on downstream applications like mass spec. If you are working with high molecular weight proteins, anything 200 kilodalton and above, the recommended gel is the new page Tris-Acetate gel that will provide optimal separation and transfer of high molecular weight proteins, thereby increasing sensitivity of detection during Western blotting. If you are working with low molecular weight proteins, anything 30 kilodalton and under, the recommended gel is the Tricine gel that is designed for optimal separation and transfer of smaller molecular weight proteins and dissolves these proteins towards middle of the gel, thereby preventing or minimizing the blow-through effect during transfer that impacts the small molecular weight proteins. If your application requires the use of non-denaturing conditions or native separation, we offer native gel options in Bis-Tris, Tris-Glycine, and Tris-Acetate chemistry. We also offer options in Bis-Tris and Tris-Glycine chemistry for isoelectric focusing and 2D gel electrophoresis experiments. For protease activity application, we offer the Zymogram or Zymogram Plus gels. If you want to try a new gel chemistry for your specific research application, the several welcome packs that we have for all our gel chemistries, gel percentages, and comb types are the best place to start. The welcome pack includes everything that you would need to start using a new gel chemistry. It includes 2 gel boxes, running buffer, sample buffer, ladder, reducing agent, and the way this package is priced, you get a mini gel running tank practically for free. All of your welcome packs can be found at the website listed here, which is thermofisher.com/proteingelwelcome. So in the next few slides, I will quickly go over the improvements we have made to precast gel options in the last few years. All of our Tris-Glycine mini gels now come with a wedge well feature. The wells are shaped like a wedge, which allows you to load up to 60 microliter of sample per well. This image shows that a wedge-shaped well enables loading of 60 microliter of samples with ease, which can't be achieved with regular wells that other vendors have in their precast gels. The Tris-Glycine wedge well gels have also been optimized to produce superior band quality and reproducibility. As you can see from these representative images, the no-wedge Tris-Glycine wedge well gels show superior performance compared to Bio-Rad TTX gel which exhibit smiling and band distortions compared to Tris-Glycine wet gel gels. All of our bold Bis-Tris gels are also available with the wet gel feature. The bold Bis-Tris gels can not only minimize protein degradation and modification, but they have a fast runtime of 22 minutes at 200 volts, and it enables loading up to 60 microliter of samples. The wet gel format of our Invitrogen bold gels allow easy loading of larger sample volumes of up to 60 microliter without any spillover. On the contrary, a Bio-Rad TGX gel shows significant sample spillover at half the sample volume. The bold Bis-Tris gel has a neutral pH and therefore results in higher sample integrity and minimal sample degradation compared to Bio-Rad TGX gel, which shows significant sample degradation of purified protein, resulting in more background on a Western blot. The band quality and resolution of a bold Bis-Tris gel is significantly better compared to Bio-Rad TGX gel, which displays smiling and distortion of bands as pointed out by the red arrows in the right image. The new page Bis-Tris gels, they have been cited in over 20,000 publications, and just like bold Bis-Tris gels are neutral pH chemistry that preserve protein integrity, minimizes protein degradation, and protein modification. And they produce excellent band quality that results in sharp, compact bands that eliminate smiles and poor resolution, which are seen with the Tris-Glycine gels. The new page gels, again, because of the superior performance, they prevent sample degradation compared to Bio-Rad TGX gel, as shown in this image. Particularly lane 2, 4, and 5, there are smears that can be seen with the same sample on a Bio-Rad TGX gel as compared to the new page gel. Now, this slide provides the comprehensive offering we have for precast gel. The Tris-Glycine gels are available in mini and midi, or the white format gel. The Bis-Tris gels are available as bold wet gel mini gels or as new page Bis-Tris gels in mini and midi format. The new page Tris-Acetate gels are also available in both mini and midi format. The Tricine gels are only available in the mini format and not available in the midi format. We also have options for native page, IEF gels, Zymogram gels, and E-page gels for high throughput applications. So we also have option when it comes to selecting the gel electrophoresis tank apparatus. We offer a back-to-back design with XL Sherlock tanks as shown in this image, but we also offer the only side-by-side design that is available in the market today for electrophoresis. The design helps you to easily load and visualize both gels during the entire gel run, provides flexibility to run one or two gels that require less running buffer when running just single gel because the two separate gel chambers within this design. The wet transfer modules, which can be inserted into the same tank, allows for optimal wet transfer without having to use a separate tank. It also uses significantly less transfer buffer, thereby reducing hazardous ethanol waste. The wet transfer module is designed to run at room temperature, which significantly reduces the prep time by eliminating need of chill transfer buffer, ice pack, ice fill buckets, which are all a regular part of the wet transfer workflow. So the mini gel tank and Sherlock tanks are compatible with all of the precast mini gels offering provided by Thermo Fisher. Okay, so here are the few key takeaways from today's talk, and that the primary being that although Tris-Glycine is the most widely used gel chemistry, it has significant limitations and should not be used for all research applications. The Bis-Tris chemistry offers multiple advantages over Tris-Glycine chemistry, and it minimizes protein degradation, amino acid modifications, and that improves the downstream application post-electrophoresis. The visual feature of Novex Tris-Glycine and bold Bis-Tris gels allow for easy sample loading with twice as much sample capacity compared to the standard wells. Our website has some very useful resources that can be downloaded, including technical handbooks for electrophoresis, transfer, and detection. There is also an interactive gel selection tool that will help in easily deciding the right gel chemistry for your research application. Thank you for your attention today, and thank you for giving me this opportunity to highlight some of the key benefits of our product portfolio.
Thank you, Dr. Tomar, for that informative presentation. We will now start the live Q&A portion of the webinar. If you have a question you'd like to ask, please do so now. Just click on the green Q&A button at the lower left of the presentation window. Type your question into the box that appears on your screen and click on the send button. We'll answer as many of your questions as we have time for. Let's get started. Our first question is, how do you ensure lot-to-lot performance reproducibility with your precast gel?
Thank you very much. Vendor has in place for ensuring quality and reproducibility of a particular gel. So to be brief, a good way to look at a quality of a particular precast gel is to look at certificate of analysis. A certificate of analysis is something that every vendor provides along with their precast gel. Sometimes it's part of the box that the gel comes in, but most of the time it has to be downloaded from the website. So I encourage you to take a look at the certificate of analysis. And what the certificate of analysis would tell you, for example, in the Invitrogen gels that Thermo Fisher has, there are a few key metrics. One of them is, the migration of 3 proteins is measured for every single lot. And these 3 proteins are myosin, which is a high molecular weight protein, 220 kilodalton, DAPDH, which is a middle molecular weight protein with 49 kilodalton, and aproteinin, which is a small molecular weight protein with 7 kilodalton. And what the quality department does, it measures the relative migration of these 3 proteins from the top of the gel, and that needs to be consistent from gel to gel, batch to batch, lot to lot. A small variation in how far they have migrated, a migration of even 3 to 4%, would result into a failure of that particular lot. Similarly, there are strict metrics for straightness, and what that means is how straight the bands are from first lane to last lane. Again, any variation of even more than 5% in that straightness would result into a failure of that gel. Curvature, which basically is if the gel is smiling or not, is also measured. There should not be any smiles when the quality is checking the gel. Any small deviation would be unacceptable. They look at physical appearance of every single gel that is packed and sent out to customers, and they look for small debris, swirls, bubbles, anything that's out of ordinary. And if they find anything, again, the whole batch gets a failure. So they have to then pass all of these metrics, and only when everything passes, they would release those gels to customers. So the reproducibility and the quality of the gel is because of the stringency that is part of the gel manufacturing process.
Thank you for that answer. The next question is, what is the shelf life of Bolt Bis-Tris gel?
Yes, so the Bolt Bis-Tris gel, because again, it's not a very reactive gel at room temperature. It can be stored at room temperature, unlike the Tris-Glycine gel, and the shelf life at room temperature or 4 degrees is 12 months.
Okay, our next question is, what type of gel do you recommend for small MW proteins of 5 kD or less?
Yes, so smaller molecular weight proteins, the best gel chemistry for them is the Novex Tricine gel. The reason being that the Tricine gel would help separate the smaller molecular weight proteins better and bring them away from the diaphragm, which ensures that you get better separation as well as better transfer efficiency. So the Novex Tricine gel would be optimal for those small molecular weight proteins.
Thank you. Our next question is, can a protein run a different MW depending on the SDS use? Of course, they don't mind the difference between denatured and native conditions.
Can you please repeat that question?
Sorry, yes. Can a protein run a different MW depending on the SDS used, not minding the differences between denatured and native conditions?
So if I understand the question correctly, the question is that when you use denaturing condition with SDS, so under denaturing condition, the separation is purely on the basis of the molecular weight. So for example, if a smaller molecular weight protein is going to run faster compared to a bigger molecular weight protein, and they will be separated on the gel. So that is purely decided on the molecular weight when you're using a denatured condition. In a non-denaturing condition, it's a different story where there are other factors other than just the molecular weight of the proteins.
Thank you. Our next question is, which gel would you choose, precasted gels or manually made gels?
So again, precast gels, what they offer a few advantages, right? One is the convenience, that you save a lot of time, obviously. The other thing is, with a precast gel, you can also get the gradient gels, which are very difficult to pour manually. And what a gradient gel allows you to do, it allows you to separate, 3 or 4 different molecular weight proteins in the same gel. So you do end up saving time and effort. Instead of running 4 gels, you can separate 4 different proteins on the same gel. The third thing is, precast gel, if it is from a good vendor, for example, Invitrogen by Thermo Fisher, you would find incredible amount of reproducibility in the gel. By that, what I mean is you will see your protein of interest run at the exact same position from gel to gel, batch to batch, lot to lot. There would not be much variation in how much difference you will find in the migration pattern of your particular protein of interest. You can also get less degradation and less protein modification when you're using those specialized precast gels. So there are a lot of advantages of precast gels. A manual gel, of course, it gives you the convenience and flexibility of pour as and when you need it, and it can be cost effective. So there are pros and cons, but I feel overall with the amount of convenience and reproducibility and preserving of protein samples, a precast gel would be a route to go.
Thank you for that answer. Our next question is, the blot transfer technique also can introduce variability in detection following gel separation. If possible, could you comment on this, as the type of gel used also influences transfer time, etc.?
Yeah, so that is again a good question. So a good transfer begins with a good gel, right? So there is it's completely one single workflow, right? I don't see them as two separate workflow of transfer and electrophoresis. By that, what I mean is what I've shown today in my slides is, depending upon what kind of gels you are using, what kind of sample denaturation techniques you are using, you would introduce a lot of sample modification, right, including degradation and other factors. So when your sample is degrading or getting modified during electrophoresis, now when you are using that gel to transfer on a transfer membrane, if your sample is degraded, you will see a lot of background, which would again which would affect the quality of the Western. If the protein is modified by some reasons, then it might impact the size of the protein based on the protein modification, which can add to some confusion during analysis. And if there are degradation to the extent that the protein, which is low abundance, is now really degraded to the level that it really can't be detected in a Western. So either you get really faint bands or negative results. So all of that is really tight, and it starts at running your gel. So yes, gel has a big impact on the overall transfer. In terms of transfer time, that really depends upon your protein of interest. There are gels that can play some role in terms of improving the transfer efficiency, decreasing the transfer time, but not the impact on the transfer time itself is not that much.
Thank you. It looks like we have time for one more question. Would you recommend using a more neutral pH buffer like Bis-Tris for running a native gel with basic proteins to get better migration?
Yes, so Bis-Tris gels can be used under native conditions. We do have a new page, a native gel, which is a Bis-Tris gel, and it is meant, it does not have any detergents, obviously, and it is meant for running protein under native conditions. And yes, a Bis-Tris gels would provide a better result in preserving sample integrity over a Tris-Glycine gel that is run under native conditions.
I would like to once again thank Dr. Tomar. I would also like to thank LabRoots and Thermo Fisher Scientific for making today's educational webcast possible. Before we go, I want to let everyone know that today's webcast will be available for on-demand viewing through May of 2018. You will receive an email from LabRoots letting you know when this webcast will be available for replay. Please share that announcement with your colleagues who may have missed today's live event. That's all for now. Thank you for joining us, and we hope to see you again soon. Goodbye.